My name is Jeremy Kahn. I'm a technology reporter at Bloomberg News, and it's my pleasure to moderate this next panel, which is on getting quantum computing to enterprise users. Beyond the hype, why recent quantum developments represent a tipping point for enterprise adoption. And we've got a couple people from enterprise and a couple people from companies that help enterprises start playing around with what they can do with quantum technology as it exists today. I'm just going to introduce everybody very quickly. So to my left, I've got Andrew Fursman, who is co-founder and chief executive at 1Qubit, which is a firm dedicated to quantum computing software. Andrew is a founding partner of a Vancouver-based venture capital firm, Miner Capital, co-founder of Satellogic Nanosatellites, and co-founder of CloudTel Communications as well. Next to him, I've got Dr. Will Zeng, who is a quantum computer scientist and head of quantum cloud services at Rigetti Computing, which if you guys may be familiar with, but it's a Silicon Valley startup building quantum computers based on superconducting integrated circuits and basically kind of the full software stack to run those machines. Next to him, I have Dr. Jerry Chow, who's the manager of the experimental quantum computing team at IBM Research, where his focus is on multi-qubit systems, working towards fault-tolerant quantum computing. Next to him, I have Thierry, who works at Airbus's Central Research Organization. He joined as head of the optronics team in 2014, and since late 2016, he has coordinated all of Airbus's R&D activities on quantum technologies, including those on quantum computing. Next to him, I have Dr. Thomas Strohm, who is at Robert Bosch's corporate research, where he has been in charge of quantum technologies, a field he's been working on at Bosch since 2013. Dr. Strohm is a condensed matter theorist by training, so he knows a little bit about some of the things you can use quantum computing for. My first question, which I'm going to throw out to sort of all the panelists here, and we'll go down the line on the first one, is just, why now? I mean, why suddenly should you be playing around? Why can you do this now? And why should enterprises be thinking about doing this now? Why not 2 years ago? And why not wait? Why not wait until you reach that quantum supremacy moment that I guess maybe will happen later this year, as Google was saying in their presentation. Andrew, why now?
I think there's two really important reasons. The first one is if you pay attention to what's been happening with the very early quantum computers, there have been a claim that this is what's possible with classical computers, and then it's one-upped by we can do this with our quantum machine, and then, well, now we can do this with classical, and now we can do this with quantum. And I think to many of us in the field, this has been sort of a back and forth that we've taken as is this moment here yet? But I think that what's important to understand is that many people, I think Matthias Treuer has been very vocal in this, really have been pointing out that this is what was the state of the art with classical computers a few years ago, and based on this competition, there have been a number of advances that have really pushed this up to here. So if you're doing some of these things on classical machines, and it's more than, say, 2 years old, there's been this much of an improvement motivated by the study of quantum systems. And I think most people in industry don't really care about quantum. They care about performance increase, and this field has been motivating performance increases. So I really like that, and I think the other answer is because if you're waiting for the moment when a gun is pointing at you in order to go out and buy body armor, that feels like a really, really bad move. You should be thinking about preparing for this so that the moment that the technology is really here, you can wield it. And so this is the right time to be starting to think about what you're going to do so you can take advantage of this machine right when it comes out.
Cool. Will, is it a similar answer for you guys? Or, yeah.
Well, I'll say a couple different things maybe, just so I don't repeat, but I agree with what you're saying. So one really big thing is going to happen and is happening right now. And it addresses the question that everybody always asks, which is the key question. It's not how does it work, it's not how do you build it, it's not which physical system, it's what are we going to do with it that's valuable for a business. And there's going to be a change in how we approach that question. And that change is going to occur when quantum computers exist, when we go from 0 to 1. And in particular, in these near-term applications, one of the reasons, I think really the key reason we don't have excellent answers for this is we don't have computers to work with to find those applications. These near-term applications are going to require empirical back-and-forth study working with real machines. We spent 20 years trying to develop applications on mathematical and theoretical ideas, but sometimes that doesn't work. So a good example to talk about this is how machine learning is today. In machine learning, there's a lot of stuff we can't prove. There's a lot of things we can't do analytically, and it's only because we have large GPU racks that we can test things with real data and actually see that in many cases we do better than we could have imagined from some kind of analytical analysis. Quantum computing is going to allow us to start to do that as the first systems come online in the next few years. And this is going to be a total change in understanding how to use quantum computers. So you should engage now because now is the first time that you can actually do that empirical development.
Cool. Jerry?
Yeah, so definitely I agree with what's been said so far. Other things that I'd say are really important for why now is that we need to build a real ecosystem of users, of people who are familiar with quantum computing. So last year at IBM we launched the Quantum Experience, and it's a 5-qubit quantum processor that's been online since last May. And what we learned from this project is that there's really a lot of, there's an active community base out there that's really ready and able to use quantum computing. People want to actually go and program their theories on our system, test how well it performs. In a year we've had 50,000 users, 20 external academic research papers coming out of a cloud-based platform with just 5 qubits. Then this past year, we also upgraded to an API for using your favorite Jupyter notebooks or an IPython notebook to make use of it even more. And we recently upgraded to 16 qubits. So this is really where we're starting to see people from the research community, traditionally from quantum information science, meeting with other people from the developer side. And we really want to continue to build up that community so that even when we get to the point of having, say, 50, 100, 500 qubits, that the software stack and how it's used is defined, and that it can actually be, as Will said, useful to find those actual applications by having an infrastructure there in place.
Great. Thierry, why don't you tell us a little bit about how you guys decided now was the right time to start at Airbus thinking about this?
Yeah, it's a good question. So instead of answering why now, I'll answer why not now. For us, I think we came in to this point in wanting to explore quantum computing really from the high-performance computing. So asking questions about how well could we do on some problems, how quick could we do some problems, how much shorter could we make these problems. And so in asking, what is the best technology and what is the best method to tackle that, quantum computers just seem like another answer to this very large arc of solutions. Airbus, though, coming in, did not necessarily have knowledge in-house, so there needed to be a way to tackle this, and I guess this will maybe be something we touch on later, which is the how. But so the why now is really more of an evolution in the thought process and sort of what the solutions are now. And so to come back to the why not bit, we're ready to explore all the technologies that can give us an edge for the different types of problems we have. So why not quantum computers, and to that extent, launch into it.
Great. Thomas?
So actually Bosch is already active in quantum technology since 5 years or so, but in the field of quantum sensing. And the reason is that Bosch is the largest supplier of electromechanical sensors, and these sensors, they have to get better and better every year. So we think that at some point we need quantum sensors, and that's why we are in this field. Being in this field, we also saw that there is this quantum computing, which provides a lot of new possibilities, and we are also in quantum, in machine learning, and maybe there's some connection which could help up. So this is one of the points which led us to quantum computing.
Great. I want to ask both Thomas and Thierry to talk a little bit more about what you actually are doing now to experiment with this. How did you go about thinking about the space? Who did you partner with? What did you start doing? And maybe also, what are some of the uses that you're trying to see if you can get a quantum speed up on? I mean, I think this is something else. There's lots of theoretical use cases. There's a lot of discussion about where you're going to get, all kinds of optimization problems you're going to be able to do much better on a quantum machine. But as of today, given sort of what the technology that exists now, what are you actually playing around with, and what are you seeing if this stuff can do? Thierry, why don't you go first, and then Thomas?
Yeah. So for us, the how, when the thought evolved to the point of, let's try and explore quantum computers, for a while it was a little bit disjointed. Needless to say, Airbus did not necessarily have internally this large team to really tackle the problem. We didn't have a whole department dedicated to this. And Airbus sort of took an honest look at it and said, we're not trying to position ourselves as the next big producer of quantum computers, nor do we hope to be able to lead the development of protocols. So instead, let's try and take an approach where we can sit and partner with people who do have this knowledge. The second question was, what hardware? Analog quantum computers, digital quantum computers. We heard also topological quantum computers now coming up. For us, again, the drive was always the solutions. It was always the answers that we can get. So to that extent, we decided, and this predates me actually, to invest in QCware. And QCware for us was the doorway essentially to this world. Hardware agnostic, different solutions, and then since then being able to explore different topics. So on the what exactly we've looked at, I think it's of different folds. For us, maintenance is a big issue, and the timeliness of this maintenance. Large complex systems and how to predict some of their behavior, some of their faults has also been part of what we do. And we're now, again, trying to coalesce a lot of the activities internally, Airbus, 130,000 people, to try and get these different ideas of how next to take these ideas forward is what we're actively doing now.
Cool. How about at Bosch? What's going on,
So
Thomas?
I think for Bosch the situation is very similar to the situation at Airbus. We will not produce quantum computer hardware. For us also the solution of the problem is important. And we know all these potential problems that are written in all the papers. I mean optimization, machine learning, material science, you name it. And what we are doing now, we are trying to collect potential problems in the company, relevant problems that we have in the company, and we try to prioritize it according to suitability to be solved with a quantum computer. I think that material science and what has been said 2 hours ago or so, this development of battery materials or catalysts or so, I think this will be a very important application.
Interesting. Jerry, you have the IBM kind of quantum experience. Are you keeping any data on sort of who is using that and what the use cases are? What kind of algorithms are they running? What sort of problems do they seem interested in? It might be interesting to find out because it might get a good set of what people are playing around with.
Yeah. So as I said, we've had users from all kinds of different walks of life. We have people who are more developers, people who are quantum information scientists. A lot of the results that have come out are things like testing of new codes, new quantum information codes, or demonstrating of a toy algorithm, right? But then the other aspect of it is actually education, and it's been adopted in a number of different universities as part of quantum computing or quantum mechanics courses. We've hosted a number of, we've been part of different workshops with Institute of Quantum Computing, with the NSF to basically perform outreach so that the next generation of learners, of users are adept at understanding gate model quantum computing.
Yeah, Will, what are you seeing when you also allow people to sort of play around with emulators, and you just, I guess, had some announcements this week on your hardware. What are you seeing from these early adopters? What are they playing around with?
Yeah, so Jerry and I agree very much on how we need to have the ecosystem grow, and that you need to provide some tools for this to happen. So we're an integrated company, and you might ask, if you're building hardware, why do you need to build some software? And we take this integrated approach because the first applications for quantum computers need to work all the way from top to bottom. That's why we're going to get there first. So earlier this week, we announced that we've built the world's first quantum integrated circuit fabrication facility for making these chips ourselves, which increases the rate at which we can improve our hardware. And that's linked all the way up the stack to a software programming environment called Forest. It's called Forest for an ecosystem reason. Right? And these computers really use nature to do something in its best way and to solve meaningful problems. And so that's why we've called the platform Forest, and it allows you to run quantum circuits, to pick up some Python. But I want to mention that there's one in particular layer that people don't talk about too much. It's not just, okay, you have a chip and some hardware, and that's a bottom-up development. And you have some software and applications that businesses have, and you do top-down development. The most important stuff, and this might be a controversial statement, is in the middle. Because these are going to miss if we don't have really great tooling, which is what we've tried to develop with the Forest programming environment, that goes all the way down to understanding the physics. I have this perspective because this is my background. I've worked on everything from superconducting qubits all the way up to algorithms and theory and built the software from top to bottom. And I think a lot of people underestimate how big and important the middle of this ecosystem is.
Interesting. Andrew, maybe you can talk a little bit about the use cases you're seeing from your customers, and also are they only doing stuff on D-Wave machines, which exist now, and I know you guys have a good partnership with the guys at D-Wave, although your company is sort of software hardware agnostic rather, or are they starting to play around with emulators for gate machines and other uses?
Yeah, so I mean, we have a great relationship with D-Wave. We love people who are building hardware, so thank you. Bring us your hardware. This is going to be really important as a software company to have computers to run this on. So I think that we are probably platform agnostic in the widest possible sense, in that I'm here to make some friends and probably also make some enemies, but we believe in annealing as an interesting paradigm and as a valid paradigm of quantum information science. We love the idea of learning what we've learned from seeing these annealers and trying to build digital annealers and seeing if we can do bake-offs and really let the results speak for themselves. I love the idea of playing with some of these early quantum circuits. We've been hearing some amazing things from Google and Microsoft and IBM and a number of other organizations around the world. But all that aside, we're taking a totally different approach with our partners, especially our end user partners, which is to say, let's go and find one of the world's largest finance companies. Let's go find one of the world's largest advanced materials companies. We just had a public announcement that we're working with Dow on this multi-year engagement that came out yesterday. The goal for us is to say, let's go find the problems, and then we have an instinct that those problems will be solved well by quantum computers, but we're going to let the problems guide us to the quantum computers as opposed to finding a nail and then going looking for a hammer, or wait, the other way around. Right. But you know what I mean.
Right. Absolutely. Maybe we can talk a little bit about what's sort of holding back wider adoption, and maybe you guys all have some thoughts on this. Andrew, you said it's just, there's not enough hardware out there yet, maybe one of the issues. Maybe you can talk a little bit about more some of the, when you talk to customers and they're reluctant to do something, why is that? And why are people maybe hesitant to get involved in this?
Yeah, so I think people aren't reluctant to get involved. This room is full. But what I would say is that the adoption comes from the fact that if you're one of these large companies, maybe you need some people to go and give you a hand. I think we're one of the largest software companies focused on quantum computers. We're certainly the first or one of the first. We're only 50 people. We can't go and partner with like 150 different companies and help them through. So one of our partnerships is actually with Accenture, who's in the room here, and they've lined up all of those use cases, and we're partnering with them in order to be able to address exactly this kind of bottleneck, because there are tons and tons of companies out there who are going to either benefit or really not benefit from the development of quantum computers. And we want to make sure that we can bring the types of expertise and the understanding and the knowledge and the preparation to all of them. And we're looking to partner with other groups that can really be multipliers of the types of work that we're doing.
Right. Well, you talked a little bit about software being a potential issue. What needs to happen from a software standpoint in order to drive adoption?
I could give a whole 2-hour-long lecture. It's one of those questions where when you've thought about something for so long, you need to distill it. I think what I'll say is, Alan talked about there needs to be quantum developers. I stood up immediately, and it took a while for a few other people to stand up. The real issue is who. Who's going to do this stuff? And in the near term, it still needs to be people who can work very much at the low level. So I think when people look towards developing applications for near-term quantum computers, which is, I think the biggest, knowing these is, I think, the biggest blocker towards more adoption, you need to have both the problems go all the way to, and the hardware. And people need to have transparency from top to bottom to really make that stack work together. And sometimes you see software developed that's very modular. There's a tendency to want to modularize. But I think the very first applications are going to need to go from top to bottom. And that's a big challenge. If you look at the software stack for your iPhone or your CPU, it's got hundreds of layers that no one person understands all of. And where we are in quantum computing right now is we need to invent that whole stack and sort of convince some of the physicists on the hardware side that their experimental code isn't that stack.
Right. Jerry, what do you, from your perspective, what do you think it's going to take to get this into the mainstream more?
Yeah, so I think that, well, with regards to the adoption and really thinking about how do we make our devices more useful, in the end, it's still making sure that we have the best quality of devices and that the software stack is in place to support it. That middle ground that Will spoke about, or where you're below you're kind of in this quantum intermediate representation, there's all kinds of things that we need to figure out. How much do you expose to users out there to know about the pulse shape or the timing? And so there's things that are hardware relevant that people in the lab and who run experiments understand, but how many people out there, how many of the quantum developers need to know, and how much of that needs to be unlocked in order to drive further explorations and further development?
And that's still sort of an open question about how much of that needs to be unlocked? Or do you think the answer is not, from other fields of computer science, the answer is as little as possible so that people can sort of just program on the top layer and not worry about what's actually going on below?
Yeah, I mean, the thing there is like, there's always the risk of unlocking too much, and what you want to be able to do is make something that's usable and adoptable and widely and understandable, right? It's like thinking about all the features that you need in an iPhone, for example.
Right.
And we've both taken a stab at this. It's not like these are totally open. We both have intermediate representations, these kind of quantum assembly things that are open that people can develop on. These are drafts. We're not sitting here saying like we don't know how to get started, right. but it is something that needs to be focused on.
Right. I want to ask Thierry and Thomas just how you get kind of buy-in from your management teams to go out and start experimenting with this stuff, and then how do you plan, assuming you can get some good results, to get them to invest further in it? Because I think often for people who maybe aren't focused on this area, and in some organizations, they might not, if you went out and said, I want to invest in quantum computing, they might look at you like you said, I want to invest in a TARDIS or something. I mean, you might get that kind of reaction. But Thomas, what you had a good answer when we were talking before on this.
So I think my management has a very positive attitude towards quantum computers, but still that does not mean that they are just pouring money into this field. So the most important thing is to come up with a list of real-world problems and at least some indications that a quantum computer could help us in solving this problem. And once this is done, the management really will pour money into this field.
And Thierry?
Yeah, I couldn't agree more. I think for Airbus, the management there also has the right mindset. Investment was made early on, and there's certainly a willingness to see where this can go. But I think, as Thomas just said, the need for demonstrating some real benefit is going to be the key marker. And ultimately, what they want to see is not so much how much more money do you need, but really what is the one difference? Can you show me one area where you've made a real world impact using this quantum system, and can you then show me if I extrapolate this forward in time, what kind of an improvement can I expect in, say, a medium term, the 5 to 7 year mark from that?
Right. I want to take questions from the audience before we run out of time. So, questions from the audience? Yes, this gentleman here, his hand up fast.
Yes, thank you. So this is a question mostly for Thierry and Thomas. And it's also something you alluded to, Will, a couple of times with Forrest and everything else, which is the question of a quantum operating system. So the idea that everybody who might not speak or be able to understand quantum can still code quantum. Would that be something that you would be willing to adopt, that you're anticipating, or do you say, well, there's so much consulting out there, we just outsource everything? What would be your initial ideas? Maybe they change in the future. I just want to hear your take on this. Thank you.
So if I understood your question, it's really about strategy and what kind of direction Airbus in this case takes in terms of strategy. To be honest with you, I think it's maybe a little bit too early to say. I think, again, the key marker for us is to try and ascertain what areas and where are the difference makers. What are the areas where we're going to see a clear benefit coming from quantum computers? And once we've assessed that, once we've seen that, I think the metric of that, the importance of that, will exactly bleed into that decision. Do we then bring things in-house? Do we develop a team? Do we develop a whole department? Or do we still kind of operate via an external company?
I think we will develop things in-house. And we already started a little bit with this because, I mean, we have a lot of computer scientists and some of them, they have difficult problems. And now they have to tell us which problems could possibly be solved with a quantum computer. And for this reason, they need a little bit idea about quantum computing. And we started by educating computer scientists in the company.
I just wanted to quickly also add that one of the things that's so great about getting involved now is that the scale of these companies is so big and the potential for quantum computing is so great, but a big check right now to get involved in this stuff, if people are investing in like the $5 million or $10 million range, that's huge for companies like ours. So the ratio of potential benefit to cost to get your fingers in the pie right now, I think is something that's pretty easy for people to get their heads around at this scale.
Interesting. Other questions? Anybody else got a question? Yep, there's a gentleman there.
Will, are you going to open source your stuff, man?
Oh, great question. Our client libraries are all open source. Apache 2, Python, we've got more stuff. Please make pull requests. I think it's super important to have that available so that companies that adopt it can really see the guts of it. The best way to learn is to see how it works and play with it.
Cool. Other questions? Oh, there's someone there.
So maybe for all of you, what do you think will be the one problem where a person who wants to solve a certain question will first go to a quantum computer to solve it rather than going to a classical computer to do the same task? So what will the problem be and when will it happen for all of you?
I was going to say like one-word answer.
Yeah, exactly. Why don't we just go down the line? Start with Andrew.
Catalyst design and soon.
Will?
Catalysts.
Yeah, I mean, chemistry.
Thierry?
I think taking an Airbus perspective, I would expect that answer to be really on hybrid solutions, some type of overlap between classical means and quantum computing.
Sincerely, I have no idea.
A little follow-up question there is, have you talked to a chemist about how they feel about this question?
Will?
Yes, and we've hired some, and we'll hire more, and we'll work with more. One of the reasons I'm able to say that I think it's going to be catalysts is that the quantum chemistry community, the classical computational quantum chemistry community, has started to get excited about quantum computing, and there are experts in that field that are now doing research in the application side who are really, top of that field is starting to get interested, and that's a really, really good indicator, both that there's some potential, but also that there's resources that we can draw on in the domain.
Jerry?
Yeah, I mean, with chemistry, really, I think there's been a lot of both experimental and theoretical work in the past few years. We recently were able to show the ground state energy of lithium hydride and beryllium hydride. But then also you start seeing where the experiment fails and what's wrong, right? You realize that you need things like error mitigation. And so how do we actually build all these things in? How do we develop better theories and apply some of the concepts of error correction and fault tolerance in a way that's useful for these short depth algorithms? There's a lot of people starting to think about that. Some of the brightest minds, who traditionally think about, error correcting codes are now thinking about this, and that's really exciting for the field of trying quantum chemistry on our quantum processors.
And we shouldn't be arrogant about computational quantum chemistry. We're not going to just come out with a small quantum computer and totally obviate everything that's happened in that field. But that's where I think we'll start to make impact the first.
Cool. I think we have time maybe for one last question, if anybody from the audience has another last one. I've got one. Oh, Jason. I can defer to Jason if he's got a question. I can ask the panelists later. Jason, go ahead.
I'm just wondering, and it's going to be possibly difficult for you to answer, some of you to answer, about the sort of proliferation of software platforms, of hardware platforms, of this kind of, letting at least a couple of dozen flowers bloom, if not 1,000 anymore, At what point the field is going to kind of have to start narrowing these things down? At what point, when the interest is sufficiently high that you have to kind of like corral things into one approach and kind of muck in with one hardware or software platform?
Yeah, Jerry, if you have
well, so for our software stack, we've really worked to try to define various different layers so that at some point you can also, we can support multiple backends, be it different type of, different simulators, different sets of superconducting qubits, different arrangements of superconducting qubits, or even other types of qubit systems. And then on top of that, that's where everything is more open source, and I'd say that there's a lot of room for that to kind of morph and see what are the best of all the different options out there and become something that eventually is more of a standard used throughout the community.
We're doing the same thing, same kind of layers. Our two systems can play together. You're in a prototyping phase for each of these layers. We're not ready to standardize. I think we're several years away from standardizing. I think you cannot standardize until you have an application to target the standards towards. So we need to first find those applications so we can evaluate whether the standards are good or not.
Andrew?
I was just going to say, it's a question like how much money is too much money? I don't know, but that's not my problem.
I was curious, I'm curious just for Thierry and Thomas, is there a concern that you will kind of get too far down the road with a vendor that then does not end up being the kind of winner of this race?
Again, I think for us, we're coming in and we're really trying to understand what are the benefits for us. I think in our case, we really wanted to take kind of an aerial view of it. We didn't want to get bogged down in any one hardware solution. We have to, of course, not that all the knowledge doesn't lay inside the Airbus, so we have to, trust and build relationships with external people who are able to talk to these top layers of existing hardwares and be able to address these problems. But I think ultimately for us, it's not so much the wild field of possibilities and potential solutions, but really capturing the one or two that are going to make a difference for us.
Thomas?
So basically, I have nothing to add to what Thierry said. So we are focusing on the problems and not on the quantum hardware, and this is why this is not a problem for us in the moment.
Great. Thank you so much, guys. I really appreciate it. You've been a wonderful panel.